All right, so we're going to talk through kind of the culminating type of projectile problem you'll probably see if you see a projectile problem in the future. So this is what we call one of those like real deal problems where you have something being launched from a surface above the zero position point and then landing back down on the ground at what we'll call the zero position point. So we've got a stone being thrown from a 45-meter tall building at a 30-degree angle above the horizontal with a velocity of 20 meters per second. So let's just diagram this to start off with because that helps us kind of visualize the process. We've got a building here. We're going to throw the ball up, or the stone up, and then it's going to fall back down. And this height is 45 meters. So the first thing we're going to do is we're going to look at, okay, what are our two components? So as always, we want to make sure that we know our x and our y values. And we're going to see what we need to kind of figure out here. So the first two are how long is the stone in the air and how far from the base of the building is it going to land. So those two components are all about the total time or distance. So what's happening the whole time the ball's in the air. The last one is about the highest point. And that highest point one is a little bit different. So we've got an apex XY chart that we can also make. And the reason that I kind of split that up is because this is not a symmetrical flight path. And so as a result, you've got some different values that get plugged into your XY component for the total time one and at the apex. And so that kind of changes what you can use, what equations you can use to solve for different variables. So let's take a look at the first part, what we need to do. We know that it's being launched at a 30-degree angle. So this is 30 degrees. It says above the horizontal. So you take your horizontal and you just lift it up and you go 30-degree angle above that point. And it's 20 meters per second. So using my trig rules, SOHCAHTOA, I know that my Vx is going to be cosine 30 times 20, and my Vy will be sine 30 times 20. All right, so that's kind of the first thing that I want to do. So when I plug these values in, I've got cosine 30 times 20, and I get a value, sorry, I was in degree or radian mode. So you always want to make sure you're in degree mode here. So you want to make sure that it says 30 degrees. So you put yourself in degree mode on your calculator. Always make sure we're doing that. Cosine 30 times 20, 17.3. So we got 17.3 meters per second. That's our Vx. I'm just going to go ahead and write this in our x column instead of doing that. So I've got a Vx of 17.3. And my Vy is sine 30 times 20, which is 10, because sine of 30 is 0.5. Probably could have done that a little bit faster in my head. Vy is 10 meters per second. Okay, now there's some other values that I know. If I'm looking at the total time that it traveled, I know that my acceleration in the y direction, and I'm just going to use negative 10, is negative 10 meters per second squared. Perfect. I know that my delta y is actually going to be negative 45 meters. So I can say it's negative 45 meters. Boom. I don't know how long it's going to be in the air, and I don't know how far away it's going to go, or how long it's traveling sideways. And remember, the bridge and the key that we want to use here is that the time it takes to travel sideways is the same as the time it takes to fall down. So this time for the y component and time for the x component are the same value. There's one thing that I could do that would make it go relatively quickly. And the one thing I could do for this column is I could use the equation delta y equals VIT plus 1/2 AT squared. And what I could do then is just say, okay, negative 45 equals 10t plus 1/2 negative 10t squared. And if I turn that into a quadratic function, I get 0 equals negative 5t squared plus 10t plus 45. Boom. I can then use the quadratic equation, and I'll end up with my time value there. So that's the fast way to get the time. That's the faster way to get the time, making sure that you keep your negatives in the right place to ensure that when you plug it into the quadratic equation, you get the right values. I just showed you this setup. I'm going to actually do the longer way, which is also going to get us to help us find this highest point. All right, so let's jump over to this apex side. Let's jump over to the apex side. The nice thing is that our Vx is still going to be 17.3 meters per second, and our Viy is still going to be 10 meters per second. Didn't change anything about how the stone came off the building in the first place. But I know my acceleration is negative 10 meters per second squared still. Now at the top, I don't know what my delta y is. I don't know what my time is, but there is a value that I do know, and that's my Vfy. I can say that is equal to 0 meters per second, because right at the top, you're going to end up with no velocity in the y direction. That's where it stops and then starts to come back down. So it's at that very top point where it stops and has no y velocity. So can I figure out some other values here? Well, what I really need to know is I need to know my highest point, my delta y. So to find that value, I can say Vf squared equals Vi squared plus 2a delta y. And when I do that, I should get 100 divided by 2 divided by 10. Should get 5 meters. So it's going to go an additional 5 meters above that building. So my delta y is 5 meters, but that's from the top of the building. So my highest point is really going to be 50 meters. Boom. So I've solved one of the parts of the problem now. I've solved the highest point part. Now I'm going to use this apex part to help me find the total time. It's a little bit of a different way than using the quadratic equation, but it's still going to give me the same values. Can I find the height or the time to the highest point? Well, for that one, I would use Vf equals Vi plus AT. And when I plug my values in there, I get a time of 1 second. Boom. I get a time of 1 second. Now that's how long it takes to go boop, 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 right up to this point here. It takes 1 second to get to that highest point, because if it's got 10 meters per second of initial velocity upward and negative 10 meters per second squared of acceleration, that means every second it takes away 10 meters per second. So after 1 second, it's going to be at the very top and have 0 velocity. So now I know that it takes 1 second to fall or to get to that highest point. What I'm going to do now is I'm going to say, okay, I know my delta y from this point is 50 meters. And I'm going to find an additional time to say delta y equals VIT plus 1/2 AT squared. But now, since I'm only talking about the part that it's falling down for, because I already found this time here, I already found this part, I can find this time, and I can say my initial velocity is actually 0, because I've cut the problem not necessarily in half because it's not symmetrical, but I've taken the upward part and downward part and kind of split them. So I'm going to say, okay, my delta y is negative 50. My initial velocity was 0, so this part goes away, equals 1/2 negative 10 t squared. And I'm going to solve for t there. All right, I'm going to solve for t. And when I do that, I get 50 times 2 divided by 10 square root of 10. And that is 3.16 seconds. So that's the time to fall down, plus that 1 second means that the total time is 4.16 seconds, which means that's how long it's in the air, 4.16 seconds. Boom, I've got another answer here. And then how far from the base of the building? Well, it's 4.16 seconds. I know that my velocity times time is my delta x because I know that in the x direction there's no acceleration or anything. So my change in x equals bx times t. That's essentially this equation here, except you have 0 acceleration, so it's just delta x equals vx times t, because your initial x velocity is your final x velocity, is your total x, or is your average x velocity. It's the same the whole entire time. So when I do that, I get 17.3 times 4.16, and I get 71.96, so we'll just round it up to 72 meters. Hopefully this kind of walking you through the thought processes that I have, helping you identify kind of which variables you know, which equations to use, how I picked out those equations. Hopefully this has been a little bit instructive for you, and you can use this as a resource when you're solving problems with projectiles at angles, or projectiles, any sort of projectile problem you have, by just thinking through which values you know and how you know them. Have a good one.